Hello, my name is Samantha Allen, and I'm a John Wesley Young Research Instructor at Dartmouth College. Let me start by thanking the organizers for putting together such a great seminar. I really enjoyed so many of the talks, and I'm excited to share my work with you all here in this format. Today I'm going to be talking about work which is joint with Chuck Livingston about unknotting knots with a single full twist. From a knot theory perspective, this problem is motivated by a theorem of Oyama, which states that any knot can be unknotted with two full twists. And for those of us interested in unknotting operations, the obvious follow-up question is, well, if every knot can be unknotted with two full twists, which ones can be unknotted with a single full twist? And it turns out that if a knot can be unknotted with a single full twist, then it's interesting to figure out in what ways this can happen. In particular, is that twist positive or negative, right-handed or left-handed? What is the linking number of the twist, which I will define carefully here in a moment, and how many different twists will do? And just to get us started, let's see an example. So here I've drawn the trefoil knot 3 different ways, in each case with a linking circle. So let's focus for now on this picture here on the left. This linking circle, what I'm indicating here is that I would like to grab those strands, pull them out, add a full, in this case, left-handed twist, like so. And in fact, when I do it in this case, I will get the unknot, which tells me that the trefoil knot can be unknotted with a single full twist. In this case, it's left-handed or negative, and the linking number of this twist is 2. And this linking number is just how many times algebraically this circle links the knot. And you might say, well, that could be a -2 as well. So by convention, let's go ahead and orient everything so that linking number is always non-negative. I can always do that. And so I see that for the trefoil knot, I can unknot with a negative twist of linking number 2. The second picture is just another version of the trefoil knot, another diagram. And if I grab these strands here and add a left-handed twist, again, right here at in this area, then I will actually get an unknot again. Okay. And if I grab these 2 strands like this and give a full right-handed or positive twist, the effect will be to change this crossing, which will again unknot the trefoil. So I see the trefoil can be unknotted with a single twist in 3 very different ways. And I want to introduce some notation so that we can write this down more succinctly. So given a knot K, let's define the set of unknotting twist indices, U of K, by the following rule. A value L with a superscript of plus or minus is in the unknotting twist indices set for K if and only if I can unknot K with a positive or negative full twist, right-handed or left-handed. That will give me the superscript of linking number L. So for example, we just computed that the unknotting twist indices set for the trefoil contains the values 2 minus, 3 minus, and 0 plus. It will in fact turn out that this inclusion is an equality, but of course that involves ruling out every other possible linking number with sign. And that takes quite a bit of work and is a lot of what our paper is working towards. Just to give you 2 more examples, it's not so hard to show that the figure 8 knot can be unknotted with a left-handed twist of linking number 2 and of linking number 0. Because it's amphichiral, that will also give us these 2 linking numbers with signs And again, it is a little more difficult to show that this is an equality rather than an inclusion. And finally, just so we have an example floating around, it turns out that the 211 torus knot is not able to be unknotted with a single twist. Its unknotting twist indices set is empty. And we'll see towards the end why this is true. So what I'm going to talk to you about today is, for a given knot, what does this set of unknotting twist indices look like? And let's start with one of our basic results towards the answer of that question. For a given knot, it turns out that there are integers m and n greater than 0 such that the unknotting twist indices set for k is a subset of a set of this form. So what does this mean? This means that if k can be unknotted with, say, a negative twist of non-zero linking number, then, well, there are at most 2 such values, and they're 1 apart. The same thing for a positive twist of non-zero linking number, and then it may also be possible that the knot can be unknotted with both a positive and negative twist of linking number 0. But it turns out that if you have a knot that actually has 6 different values, so all of these values for some m and n, then it must be of this form. In particular, m and n must equal 1. I'm going to try to sketch the proof of this for you. It involves various tools from Heegaard Floer theory, but it starts with a simple fact, which is that if a knot can be unknotted with a single twist of some sign and some linking number, which is non-zero, then some integer surgery on that knot bounds a rational homology 4-ball. This allows us in particular to use tools like the Ajvat-Szabo D invariant to study this problem. So the D invariant associates to a rational homology 3-sphere Y and a spin C structure T on Y, a rational number. And in particular, if an integer surgery on a knot bounds a rational homology 4-ball, which is exactly the case that we would be in here, then, well, if that linking number is odd, then some values of the D invariant must be 0, and the same if L is even. So this gives us some starting criteria, some things we can use as obstructions for values being in the unknotting twist indices set. If we add on to this the VI invariance of ni and wu, this is a sequence of invariants of which are non-negative integers, which is non-increasing and at each step decreases by at most 1. Then combining what we know about the D invariant in this situation, we can say, well, for some values of I, and within those values of I, for some values of L, the left-hand side of this equation will be 0, and we get restrictions on the VI invariance. It turns out that this sequence of VI invariants does eventually hit 0. Remember, it's not increasing. It does eventually hit 0, and so it remains 0 for the rest of the sequence. If we let nu plus be the minimum index where VI of k equals 0, so the first place where we hit 0 in that sequence, and we stare at what this relationship here tells us, then we get a statement like this. So if a knot k can be unknotted with a single negative twist of linking number L, which is greater than 0, then L is in between these two values depending on nu plus of k. So this is nice. I get a restriction on L that just depends on this one value. And it's especially nice if you stare at this long enough, you'll realize that the gap between this value and this value is at most 2, which means, in particular, if K can be unknotted with a single negative twist of linking number L, then there are at most 2 values where that can occur, and those 2 values of L are at most 1 apart, giving us these 2 values in that result. Because this theorem cannot take care of linking number 0, we also have to allow for this possibility. This portion comes from the following fact, which is not so hard to see, which is that if a value is in the unknotting twist indices of K, set of K, then the same linking number but with opposite sign, so the opposite direction twist, is in the unknotting twist indices set for the mirror of K. And in fact, this is an if and only if statement, but what this says is that if K can be unknotted with a positive twist of linking number L, then negative K can be unknotted with a negative twist of linking number L. And of course, by this theorem, there are only 2 ways that can happen. So we see that the positive twists, there are only 2 options and they're 1 apart as well. So that's essentially the proof of this theorem. I should mention that aceto and Gola have a similar result in a much broader setting. What this theorem tells us is that if we know the VI invariance for the knot, or if we just know its nu plus invariant, then we can really narrow down the values in its unknotting twist indices set. In particular, if we look at the set of alternating knots, we know a lot about their VI invariance. It turns out that for an alternating knot K, its VI invariants are equal to those of some 2N torus knot. And the VI invariants of the 2N torus knots are really nice. They are easy to compute. And so if I take an alternating knot, I can compute its signature, figure out which torus knot to compare it to, and use those VI invariants to get the following result, that if an alternating knot K can be unknotted with a negative twist of some non-zero linking number, then L must be in the set 1, 2, 3, 4, and 5. If in addition I know a little bit more, which I will share with you here in a moment, it turns out that 5 is not realizable either. So let's say it turns out that L cannot be equal to 5. This is a really interesting, this portion is a really interesting result. It has a nice proof, which uses a totally different strategy, but still starts in a very kind of reasonable way, which is the following lemma, which I believe is an exercise in Gomp and Stipschitz, which is if a knot can be unknotted with a negative twist of linking number L, then there is a knot J and an orientation preserving homeomorphism from L squared plus 1 surgery on K to negative L squared minus 1 surgery on J. And the idea for this is to start with this surgery, do a blow up, and then a blow down, and you land at something like this. So we have this relationship between these 2 integer surgeries on various knots. And so what we can do is we can say, okay, I have a relationship on their surgeries. That gives me a relationship on their D invariance, if you're very careful tracing that meridian through this homeomorphism. That in turn, that also will give us then a relationship on their VI invariance, kind of using the same strategy as we did in our original basic result there. So, and we get this theorem, which looks really complicated, but actually isn't so scary. Let me talk you through it. So suppose that K can be unknotted with a negative twist of linking number L. And just for notational ease of notation, let's go ahead and let n be L squared plus 1. Then it turns out that there is a knot J prime such that for the values of I between 0 and n over 2, this V invariant of J prime is equal to some value depending on L and I and N away from VI of K. So let me just say a few things about this. In particular, this J prime is essentially negative J. This allows us to rewrite this surgery as a positive surgery on J prime rather than a negative surgery. This bracket with a subscript going on here is just an operation which takes the value inside the bracket and the subscript and outputs a non-negative integer. So you see that a few times in here. And finally, this beta being different if L is even and if L is odd has to do with the spin-C structures on the surgery. So we have this relationship. It looks pretty complicated, but what it does, again, is it gives us a relationship between the VI invariance of K and the V invariance of J prime. So let's move into the situation that we're interested in. If I have an alternating knot and I look at linking number 5, let's suppose towards a contradiction that an alternating knot can be unknotted with a negative twist of linking number 5. Then if we look back at this theorem, L squared plus 1 is 26, beta is 13, and this theorem says that there is a knot J prime such that for all I between 0 and 13, so for 14 different values, the invariants of J prime are related to the invariance of K in this way. So what does this do? This gives us 14 different equations where this is just some integer and I'm relating J prime to K. If you write down all of these for linking number 5, for all the various i's, there are two which are particularly important here. I equals 1 and I equals 6. For I equals 1 and I equals 6, we get these two relationships. And if we recall what we know about the VI invariants, that they are non-increasing and they decrease at most 1 at each step, and apply that to the fact that we know what V8 of J prime is and V9 of J prime is, then we can work through this and realize that the difference between V1 and V6 of K is between 1 and 2. And it turns out because K is alternating, we can relate it to a 2n torus knot and compute some things about its VI invariance on its own. And it turns out with all of these obstructions bouncing around that we can determine that V0 of K has to be 3 and V5 of K has to be 1. In particular, K has the same VI invariance as the torus knot 213. In particular, 213 has V1 equal to 3 and V6 equal to 0. And of course, the gap between those is not between 1 and 2, and so we've reached a contradiction. Okay, so it turns out that we can rule out that case of L equals 5, and so an alternating knot can only be unknotted with a negative twist of non-zero linking number L if L is between 1 and 4. Turns out we can say even more, but I need to use quite a few more invariants. So I've been focusing a lot on the Heegaard Floer invariants that we use, but we also can approach this problem with Casson-Gordon invariants and other classical invariants. And so here's a theorem that just kind of groups together a couple of our other results. If a knot K can be unknotted with a single twist of linking number L and sign S, then we can put some pretty strong restrictions on the signature function of K when L is greater than 0 and when L is equal to 0. And if L is odd, then we know exactly what its ARF invariant has to be. Okay. So if we combine all of these things together, we get the following theorem, which is that if I have an alternating knot K, then the unknotting twist indices set for K is a subset of one of these here on the right, determined by its signature. Okay, so for example, if the signature of my alternating knot is 4, then the unknotting twist indices set is a subset of 1 minus and 3 plus. What's really interesting is that as the signature gets larger, we're able to rule out those values 2, 3, and 4 for L. And we see that the unknotting twist indices set can only have linking number 1 as an index. So if K is an alternating knot and its signature is greater than 8 in magnitude, and if the ARF invariant of K is equal to 1, notice that means that L has to be plus or minus 3 mod 8, so you're not going to get a linking number of 1. Then, well, we've ruled out the last elements here, and K cannot be unknotted with a single twist. So this does produce infinitely many knots which cannot be unknotted with a single twist. And I will say, speculatively, we feel like in general, for large crossing knots, you will not be able to unknot your knot with a single twist. There are just too many obstructions. But that's telling us a lot about these knots that don't have twists. What about the knots that have lots and lots of options for untwistings? So let's talk a little bit about knots which have unknotting twist indices set equal to 6. So let's recall from earlier in the talk that if UK has 6 elements, then U of K is equal to, on the nose, the set 2 minus, 1 minus, 0 minus, and the same linking numbers but positive twists. In particular, having both zeros tells me from signature obstructions that the signature function of K is identically 0. That's a pretty strong restriction. From the things that we know about the nu plus invariant and other Heegaard Floer obstructions, turns out that nu plus of K also must be 0, which implies that all of the VI invariants of K are 0. And so these are some pretty strong restrictions, so you'd expect this to be maybe pretty rare. But in fact, if you think about it for a second, these are qualities that all slice knots have, so that might be the first place that you look. It turns out that if K, let's write this as a fact, if K has unknotting number 1, this is traditional unknotting number now, and K is amphichiral, then, well, having unknotting number 1 actually allows you to get a 0 twist and a 2 twist of the same sign. These are the kind of twists that affect a crossing change. If it's amphichiral, then having the negative twist implies that I have the positive twist of the opposite sign. So if K is amphichiral, then we can say for sure that all of these guys are in our unknotting twist indices set. So at this point, I'm looking for an amphichiral unknotting number 1 slice knot, possibly. Okay. But what I really need is some way to get at these ones. Right now, all we have to deal with ones is the ARF invariant to rule them out, but I need a construction to say when I can get a 1 minus and a 1 plus for certain examples. And this construction was discovered by Muhammad at-Nu, which is it's a really nice construction. So here on the left, I have the knot 6-1 drawn as a ribbon knot. And it turns out that if I grab these strands, I can unknot the knot. So if I zoom in on what's happening right here and do a small isotopy, I see that my linking circle is just grabbing these 3 strands, and I want to give them a full twist to the right. And I get something like this. And if you look at this portion of this ribbon knot between these 2 strands here, you see that this clasp that was grabbing those 2 strands is now going over the strands, right? This is all under, and I can pull it over here. And so essentially what we've done with that full right-handed twist is pull this strand over, but because I have a ribbon knot with this particular type of diagram, this will, of course, once it's pulled over, completely unknot the knot. Okay. And a very similar thing can be done with a very similar diagram. You just need to add a Reidemeister 1 here and get that this same diagram can be unknotted with a negative twist of linking number 1 as well. And so if I add all of our conditions together, if I look for a slice knot with unknotting number 1, which is amphichiral and has a ribbon diagram where undoing a clasp like this will unknot the knot, then I don't quite get what I'm looking for, but I can find an example that's pretty close. So here's a ribbon diagram of the knot 8-9. This is a knot which is amphichiral and has unknotting number 1, so I know it contains, let's go ahead and write this down, 8-9 is amphichiral, it's unknotting number 1, so it definitely has the values of 0 and 2 with both signs in its unknotting twist indices set. And if you do a very similar move to the one that I just showed you, but instead grabbing in this way, so what I'm doing is I'm grabbing this portion and this portion of this ribbon diagram along with this, and a very similar type of thing will happen. It will undo this type of clasp and completely unknot the knot. And there is a very similar construction for the negative 1, but notice we don't need that construction because we know that 8-9 is amphichiral. If it has a +1 untwisting, then its mirror image, which is itself, has a 1 minus untwisting as well. Okay. So we know that this knot has size of its unknotting twist indices set 6. So we see here that we were able to meet all of these conditions and find a construction for this particular knot so that it has 6 different unknotting twist indices. But in general, we expect that to be pretty rare. These restrictions on the signature function, the VI invariance, the ARF invariant are pretty strong when you combine them all together. And so, again, in general, we do expect that for large crossing number knots, we will usually, or in general, get a knots which cannot be unknotted with a single twist. Let me just end with a couple of further remarks. Census of prime knots with up to 8 crossings found only 10 knots for which we can completely determine the unknotting twist indices set. The first example with unknown values is actually this ribbon knot 6-1 because it's not amphichiral, even though we know that it has a 0 and a 2 because it's unknotting number 1, and we know it has plus or minus 1 from this construction that I've shown you. We don't actually know if it has the 0 and 2 of the opposite sign. Okay. And there are many, many more unknown cases. And of course, in order to show that a knot can be unknotted with a single twist of a certain linking number and a certain sign, we really would need some new constructions. The case of linking number 1 in general is pretty challenging. But I've shown you this particular construction for realizing linking number 1, but it really only works for nice ribbon diagrams, and ruling out linking number 1 is really difficult, and this is because most of our invariants deal with rational homology spheres rather than integer homology spheres, and the case of L equals 1, it is just not addressed particularly well in these cases. Okay. So this is a direction that we certainly wish to pursue in the future. So I think I'll end there. Thank you for tuning in, and please don't hesitate to get in touch if you have questions or comments. Thanks.